Chapter 1, Exercise 6D. Use the previously proven parts. Step 1. Take an arbitrary natural number n. The set of integers, m element of integers, m less than or equal to nx, is bounded from above by nx. Hence there exists a maximal m element of integers such that m is less than or equal to nx. Then m plus 1 greater than nx, and dividing by n the inequality m less than or equal to nx less than m plus 1, we get m over n less than or equal to x less than m plus 1 over n. Similarly, there exists an integer k such that k over n less than or equal to y less than k plus 1 over n. By summing the previous inequalities, we get this. That is, m plus k over n less than or equal to x plus y less than m plus k plus 2 over n. Step 2. Let t s element of rational numbers, t less than or equal to x, s less than or equal to y. We have t less than m plus 1 over n, since this, and s less than k plus 1 over n, since this. In the same way as in proof of part C, step 2, we can show that b to the t less than or equal to b to the m plus 1 over n, and b to the s less than or equal to b to the k plus 1 over n. Since the last inequalities are true for any rational Ts such that t less than or equal to x, s less than or equal to y, we deduce that b to the x less than or equal to b to the m plus 1 over n, and b to the y less than or equal to b to the k plus 1 over n, by the definition of supremum and of the sets big of x and big of y. By proposition 118b, this and that, thus b to the x, b to the y less than or equal to b to the m plus 1 over n, b to the k plus 1 over n. Now, using part b, b to the x, b to the y is less than or equal to, ultimately, b to the x plus y, b to the 2 over n. For the last inequality, we use proposition 118b and the fact that m plus k over n element of rational numbers, and m plus k over n less than or equal to x plus y. Consequently, b to the m plus k over n less than or equal to b to the x plus y, by the definition of supremum and of the set big of x plus y. Hence, b to the x, b to the y less than or equal to b to the x plus y, b to the 2 over n. Step 3. Let r element of rational numbers, r less than or equal to x plus y. Then r less than m plus k plus 2 over n by step 1, and we can write r equals t plus s for some rationals t, s with t less than m plus 1 over n and s less than k plus 1 over n. Indeed, since m plus k plus 2 over n minus r is a rational number strictly greater than 0, choose arbitrary positive rational numbers epsilon and delta such that epsilon plus delta equals this. Set t defined as m plus 1 over n minus epsilon, and s defined as k plus 1 over n minus delta. Then t less than m plus 1 over n, s less than k plus 1 over n, and t plus s ultimately equals r. Using part b and the similar reasoning as in step 2, we have b to the r ultimately less than or equal to b to the x, b to the y, b to the 2 over n, since m over n less than x and k over n less than y. Thus, b to the r less than or equal to b to the x, b to the y, b to the 2 over n. As the last inequality is true for any rational t less than or equal to x plus y, we deduce from the definition of supremum and of the set big of x plus y that b to the x plus y less than or equal to b to the x, b to the y, b to the 2 over n. Step 4. First note that b to the t greater than 0 for all t elements of real numbers. Indeed, let n be an integer such that n less than t. By definition of b to the t, we have that b to the t greater than or equal to b to the n. If n greater than or equal to 0, then b to the n greater than or equal to 1 greater than 0. If n less than 0, then negative n greater than 0, and thus 1 over b to the n equals b to the negative n greater than 1 greater than 0. By proposition 115d and proposition 118e, we have that 0 less than b to the n, which equals 1 over b to the n, less than 1. Thus, in both cases, b to the n greater than 0, and so b to the t greater than 0. Denote d equals b to the x, b to the y over b to the x plus y, and c equals b squared. Note that d greater than 0 by the previous discussion, and c greater than 1 since b greater than 1. Let n be an arbitrary positive integer. From step 2, b to the x, b to the y less than or equal to b to the x plus y, b to the 2 over n. By multiplying the previous inequality by b to the negative x plus y greater than 0, and using proposition 118b, we obtain d ultimately less than or equal to c to the 1nth. In a similar fashion, we can show using step 3 that 1 over d less than or equal to c to the 1nth. That is, d greater than or equal to 1 over c to the power of n by proposition 118. Then, for every natural, n greater than or equal to 1 by proposition 118, and induction, we have 1 over c less than or equal to d to the n less than or equal to c. Step 5. Assume that d greater than 1. Choose natural number n greater than c minus 1 over d minus 1. Then, since d minus 1 greater than 0, we have that n d minus 1 greater than c minus 1, and thus 1 plus n d minus 1 greater than c. Then, using the inequality from exercise 7a, d to the n ultimately greater than c. This is impossible, and so it must be d less than or equal to 1. Step 6. Now, assuming that d less than 1, then, by proposition 118e, 1 over d greater than 1. Using the last inequality in step 4 in proposition 118e, we get 1 over c less than or equal to 1 over d to the power of n less than or equal to c. By repeating step 5 for 1 over d, instead of d, we can deduce that it must be 1 over d less than or equal to 1. That is, d is greater than or equal to 1. Step 7. By step 5 and step 6, we conclude that d equals 1. Finally, this shows that b to the x plus y equals b to the x, b to the y. Above is the graph for b greater than or equal to 1. F of x equals b to the x. If r less than or equal to s, then b to the r less than or equal to b to the s. And so the function f of x equals b to the x is an increasing function. In fact, it is strictly increasing. With exercise 6, Rudin formally introduces the definitions of what will be the exponential function. Thanks for watching.